All right, we're going to start a brand new chapter today, covering section 6.1, Introduction to Chemical Bonding. We will not finish this chapter before Christmas break. So I really just want to talk about the three types of bonds that occur. And I will post a electronegativity worksheet that will help us classify or predict what type of bonds will form between elements. So imagine getting onto a crowded elevator. As people squeeze into the confined space, they come in contact with each other. Many people will experience a sense of being too close together. So when atoms get close enough, what do you think happens? Well, think about their electrons. Okay, their electrons have a negative charge, so their outer electrons will repel each other. But at the same time, those outer electrons are strongly attracted to the nuclei of the atoms that they're close to. So the degree to which these outer electrons are attracted to other atoms determines the kind of bond that will occur. All right, so today's objectives. Talk about what a chemical bond is, why most atoms form chemical bonds, the difference between ionic and covalent bonding, why most chemical bonding is neither purely ionic nor purely covalent, and then classify the bonds based on their electronegativity differences, which was a vocab term from chapter 5. Okay, so atoms in nature hardly exist as independent particles. They are usually bonded with another element because they're highly reactive. Okay, it's very rare if you find something like pure or by itself. So the definition of a chemical bond is a mutual electrical attraction between nuclei and valence electrons of different atoms that binds the atom together. All right, so atoms form compounds by either gaining, losing, or sharing electrons. And so now we're going to go into the different types of bonds. First bond, ionic bonding, the electrical attraction between cations and anions. Electrons of one atom are going to either give up and it's going to be transferred to another atom. Covalent bonding results when you share electrons between two atoms. And so the shared electrons are actually owned, and I guess I shouldn't say equally, by the two bonded atoms, but they are shared. And we'll talk about the difference between being shared equally and unequally. So electrons are basically redistributed in ways to make the atoms more stable, either by transferring that electron or by sharing that electron. So I have some visual concepts here.
Ionic bonds begin to form when an atom whose outermost energy level is almost empty transfers an electron to an atom whose outermost energy level is almost full. The two atoms are strongly attracted to one another and bond because this new situation changes the atoms to ions of opposite charge. Particles of opposite charge are attracted to each other.
Okay, so that was ionic bonds. Here's covalent bonds.
Many atoms form covalent bonds. In covalent bonds, electrons are shared by both atoms. The first energy level in atoms can hold 2 electrons. By sharing electrons in a covalent bond, each hydrogen atom has a full outermost energy level. Water molecules are also held together with covalent bonds. Again, we see that covalent bonding gives each atom a full outermost energy level. The outermost energy level for hydrogen can hold 2 electrons. The outermost energy level for the oxygen can hold 8 electrons. In covalent bonds, the shared electrons move between the atoms that share them, forming a single electron cloud around both atoms.
Okay. So how do we determine which bond occurs? We have to look at their electronegativity values. And so I'm going to show you a table later on, just basically it shows the electronegativity values of each element in the periodic table, but there are 3 classifications: nonpolar covalent, polar covalent, and ionic. In nonpolar covalent, we are sharing electrons, but we are going to share them like equally. There's a balanced distribution of electrical charge. And so if we think back to the definition of electronegativity, I believe it was the attraction for another atom's electrons. So here the electrons will be shared equally. In polar covalent bonds, the atoms are going to have an unequal attraction for their shared electrons, which means they're going to share them unequally. And as a result, we're going to form a dipole, or a slightly negative end and a slightly positive end, because the electrons will hang out more with one atom, thus causing a slightly negative end, versus another atom, causing a slightly positive end. And then ionic, where the electron is actually just going to be transferred. So here are the electronegativity values. When you look at the values of the atoms involved in the bond, you'll subtract them and look at the difference. And if you have a difference of 0.5 and below, we call it a nonpolar covalent bond, where there's even electron distribution. If it's between 0.5 and 2.1, then it's going to be polar covalent, where the electron is still being shared, but it's an unequal sharing, and as a result, you get a dipole, where the electron hangs out with one atom more versus the other, thus causing a slightly negative charge and a slightly positive charge. And then if it's anything 2.1 above, then it is ionic. Now you may be wondering, well, what happens if it's exactly 0.5 or exactly 2.1? Well, ionic bonds tend to be metal and non-metal bonded together. So if that's the case and you get exactly 2.1, it's probably going to be ionic. As for the 0.5, you might have to look at the structure of the atom, but I don't know. I guess I can't really mark it wrong. So, all right, let's take a look at the electronegativity differences of hydrogen halides here. So hydrogen and fluorine, if you subtract the two, I know fluorine off the top of my head is 4 and hydrogen's 2.5, and that can't be right, 2.1. How did they get 1.8? It should be 1.9. Anyways, when you subtract the two, you get a difference of 1.8. So where on the scale what type of bond would this form? Well, I hope you said polar covalent, right? 1.8 is about right here. Hydrogen and chlorine, the electronegativity difference is 1. So what kind of bond are we looking at here? Again, that's polar covalent. Hydrogen and bromine, when you subtract the two, is 0.8. What kind of bond are we looking at here? Polar covalent. And then hydrogen iodine, 0.5. Oh, it could be non-polar covalent, but because it's just those two, it's probably going to be polar covalent. Okay, so that was really boring, but just wanted to show you the table. Okay, there was another thing I wanted to talk about. So if you take a look at the electronegativity difference and the bond energy involved, bond energy is the energy required to either form or break that bond. So if you want to form this bond, you're going to need 570 kilojoules per mole to form it. If you want to break it, you're also going to need 570 kilojoules per mole to break it. But what do you notice about the bond energy and the electronegativity differences? I hope you see a trend that the higher electronegativity difference you see, the higher your bond energy is. Okay, and the lower your electronegativity difference is, the lower your bond energy is. So just a trend I was hoping that you'd notice. So recap, nonpolar covalent bond means we're going to share the electrons equally. So there's really it's an uncharged compound or molecule because the electrons are going back and forth equally and being shared. So here is a nonpolar covalent analogy. 2 polar bears sharing ice cream, or 2 penguins sharing ice cream. It says the clearest examples of nonpolar covalent bonds are those between identical atoms, such as hydrogen gas, nitrogen gas, oxygen gas, or chlorine gas. Bonds between atoms with nearly the same electronegativity values, such as carbon and hydrogen atoms, are usually also considered nonpolar. Remember, this is usually a continuum, and conventional distinctions are somewhat artificial. So in this analogy here with the polar bears eating ice cream and the penguins eating ice cream, what does the ice cream represent? It represents the electrons. What do the polar bears and the penguins represent? They represent the atoms involved in the sharing of the electrons. Moving on to polar covalent, okay? Because the electrons, let's just take a look at water here. Because the electrons are hanging out with oxygen more, then we are going to have a slightly negative charge, and those electrons aren't hanging out with the hydrogen, so hydrogen has a slightly positive charge, so we get that nice little dipole here. Same thing with hydrogen and fluorine. There's that sigma positive for hydrogen and sigma negative for fluorine. Another way to show dipoles with arrows. So the arrow points more towards the negative atom, and then you put like this little line here to represent kind of that plus sign. So this atom is more positive and this atom is negative. The electrons are hanging out more with fluorine. So it says in a polar covalent bond, two atoms still share bonded pairs of electrons, but those electrons are decidedly more attracted to one atom than the other. Examples include bonds between carbon and oxygen atoms, or between hydrogen and fluorine atoms, as you can see down here. So you can see they're sharing, but it's unequal, and he's not too happy about it. Okay, some examples between hydrogen and fluorine and hydrogen and iodine. You can just kind of see that they are both polar covalent, where here we're looking at nonpolar, they're being shared equally. All right, carbon fluoride is nonpolar. Okay, this slide is representing that shape also plays a role. So this is called a tetrahedral, and we'll get into this later on this year, but all of them are pointing to the fluorine. So fluorine is more negative than the carbon. However, because of the shape of this molecule, I can't cut it in any way to get a positive end and a negative end. Okay. Now this molecule is polar because hydrogen's the least polar, or the least attraction for electrons, and carbon is a little bit more, and then fluorine really, really loves electrons. And so here we can definitely see a distinction of a positive and a negative. So even though this is a tetrahedral, but because the way the charges are laid out in the different types of atoms, I can cut this molecule in half and get a positive end and a negative end. So shape does play a role. All right, let's take a look at a sample problem using electronegativity values listed in figure 20, page 161. So we're going to classify the bond in between sulfur and the following elements. Now, if we look at the difference here, sulfur is 2.5 and hydrogen is 2.1. The difference is 0.4. So if we take a look at this scale, it should be a nonpolar covalent. Which one of these atoms, sulfur, the 2.5, or hydrogen, the 2.1, is more negative? It would be the sulfur. Okay, so the electrons are hanging out with sulfur more. Cesium, we look at the electronegativity table. And I just realized I never went back to full screen here and my Mac's going to die, but I think I can do this. Sulfur is 2.5, cesium's 0.7. Subtract the 2, you get 1.8. So what type of bond do we see here? Yeah, okay. Yes, sorry. Polar covalent, okay? I think I just mixed that up, sorry. It is 4:24 in the morning. It's polar covalent, and the more negative atom, again, is sulfur. Now, chlorine and sulfur, chlorine's 3 and sulfur's 2.5. You subtract it, it's 0.5. It's nonpolar covalent. And then the more negative atom, however, is going to be chlorine. All right, so that does it for 6.1. Kind of went through electronegativity pretty fast, but the worksheet will post. If you have questions, I hope to be back on Friday, tomorrow. But if not, you can always email me. You can also just make comments on Google Classroom, and I'll be happy to answer.